Which comes first, the equation or the idea? What is mathematics? It's basically the language of quantities. It's kind of like Sanskrit is the language of properties. Okay, I want to work out something that was confusing me the other day. We set up a 9-volt battery and a little bitty lamp. Didn't draw that very well. Let's see if I could draw it three-dimensionally. There we go. Boop. A little lamp and a 9-volt battery, and it lit up because the current went through here, went through a little filament. Erase that. And what happened? What was the usually these bulbs are measured in wattage, and the key formula for wattage is that power in watts equals voltage over, no, equals voltage. Wow, it's not, okay, it wasn't responding. Power equals voltage times current. Now, the thing is about this thing, if I have 1 watt, if I've got 12 watts going across it, so a 12-watt bulb is going to have, and if this is a 9-volt battery, and then it's going to take about 12/9 of a amp to go through there. Here's some pictures of standard light bulbs, a 60-watt incandescent bulb down to a 13-watt. The point is that, well, one point is the bulb is going to need quite a bit of current in order to light up. This is well over 1 amp here. Okay, but now let's say we stick a 220 ohm resistor over here. And this, in order for that, by the way, in order for that current to be 12/9 of an amp, that means that resistance is really close to about 1 ohm. We could actually find out if there's 9 volts, the voltage is equal to the current times the resistance. So if I plug in 12 volts is how much we have across there, and we've got 12/9 of an amp. Our resistance is going to be 12 over 12/9, which is equal to 9 amps. It's not equal. Whoops, 9 ohms. So here, I guess here's the relevant circuit diagram. We've got a 12-volt battery, and we've got a 9 ohm resistor. So first we want to find the current through the resistor, and B, find the power dissipated across the resistor, and C, okay, actually I have no idea why I used 12 volts or 9 ohms at this point. The battery we were using the other day was a 9-volt battery. Okay, I think what's going on is I'm looking for the answer to this question. When they say it's the current that kills, offhand it seems that a shock of 10,000 volts would be more deadly than a 100 volts, but this is not so. Individuals have been electrocuted by appliances using ordinary house currents of 110 volts, and the electrical apparatus and industry using as little as 42 volts direct current. I think what I would say to remedy this, it's the conductivity that kills. How can you create something that is a conductive circuit? Okay, so I'm going to look up a data point. What is the internal resistance of your typical 9-volt battery? As luck would have it, I've found a YouTube video that actually describes how to test the internal resistance of a battery. So it looks like he does this in 3 steps. First, he finds finds the voltage of the battery by setting this on voltage. Then he finds the resistance of an external load, and then he measures the current across the battery. And when he's measuring the current, he puts... Here you can see him actually measuring the current across across there. He's got the external load in series with the battery. So he's got this equation here, which says basically R internal plus R external equals the current times, or equals the voltage over the current. That in turn would come from an equation that would go, if we got, basically we've got the internal resistance over here of the battery and the external resistance over here. So I'm just going to go through this with the circuit diagrams as I would expect them. There's actually 3 resistors involved in this. One of them is the internal resistance of the voltmeter. We've got the wire, we've got the battery internal resistance, and this is what we're trying to find. Oh, but actually, this is kind of the information that I wanted right here. I mean, at the end of the day, all I was really asking for at the beginning of the video was what the resistance of the batteries. I think we were using an alkaline battery, which was 2.8 ohms. So I think we were using an alkaline battery. So our situation would have been that we had the 9-volt battery and about 3 ohms of internal resistance, and then coming across the light bulbs, which were maybe, well, let's measure those. I can't do it now, but sometime later maybe we can find out the internal resistance of the light bulbs. So Google search for types of light bulbs gives me something that looks like this. The type of light bulb we were using in class, I believe, was an incandescent bulb, and I think it might have been one of these S11s. Looks like there's basically 3 different types of light bulbs: LEDs, CFLs, and incandescents. It says here for LED wattages, 1/4 to 1/5 of the incandescent wattage value is usually close to what you want. So if you've got a 60 watt incandescent, you can replace it with a 1/5 would be 12, I think. 12, and 1/4 would be 15. A 12 to 15 watt LED light. But I think you can also use a 12 to 15 watt, what is it? CFL bulb. Now, so far as I know, that's about right. The bulb I have for my CFL bulb is about a 13 watt bulb. Why does it say here that when it comes to purchasing energy efficient lighting, LEDs exceed CFLs by a wide margin? I think it's not because of their wattage. It's because they have a faster start time, work well in cold weather, and are substantially more durable since they're made from plastic rather than glass. It says LEDs can replicate the same lighting conditions found in fluorescence while lasting longer. And this is my question: why would they use less energy? They're the same wattage. So I'm asking the question, do LEDs use less power than CFLs? To Google. As a rule, LED bulbs use 90% less electricity than standard bulbs. They have an unparalleled even spectrum of light and have a lifespan beyond 10 years. LEDs provide the most efficient way to save energy and conserve our natural resources. LED bulbs do not contain mercury, which CFLs do. Let's compare the visual spectrum of a CFL bulb. See if I can find something that looks good on the Google images. Okay, here it is. This is the visual spectrum of a CFL bulb. Which one do you like the best? This one shows everything coming up in sharp peaks. I kind of like that one. That looks more realistic than this. Looks like here is somebody that's been nice enough to draw out the distributions of the what are those, wavelengths versus temperatures. I mean wavelengths versus frequency, um, for a 3500 Kelvin color temperature versus a 5500 Kelvin temperature versus a 2700 Kelvin uh, temperature spectrum. You see that the lower the temperature, there's more red and less yellow, less purples. With the lower temperature, or with a higher temperature, there's more purple and a little bit less red. Yet this guy says incandescent light bulbs are now being replaced by compact fluorescent lights. Compact fluorescent lights, that's what CFL stands for. All over the world, they are economical, use less electricity, and are better for the environment. But before you rush out and buy a whole box of CFLs for your property, don't overlook the advantages of using LEDs instead. LEDs have a variety of benefits attached to them, which make them an attractive proposition for those wishing to save some money while having a reliable lighting for their home or business. And this is the part that I'm not quite grasping. LEDs use far less energy than CFLs. This might surprise people, as CFLs are often marketed as energy-saving bulbs. While this is true, when compared to LEDs, there is only one winner. LEDs will reduce electricity bills substantially while providing all of the light you need. So I'm going to try to see if I can find the visible light spectrum of an LED light bulb and see what the images look like for that. And here's an interesting image because it shows a whole lot of different spectra. And I like this image here because it says Spectral Distributions, plural, of LEDs by Sanjay Joshi, PhD. Let's look at that one. Sanjay says, in addition to the characterization of light by its intensity and distribution, the spectral distribution is also of interest. Light sources emit light at varying amounts at different wavelengths. Spectral distribution characterizes the light output across different wavelengths of the light spectrum. The wavelengths of visible light is between 400 and 700 nanometers. Incidentally, these also happen to be a majority of the wavelength of light that are relevant to photosynthesis. The combined effect of the complete range of radiation between 400 to 700 nanometers appears as white light to the human eye. Radiation with a wavelength of 400 nanometers generates a response in the human eye that makes it perceived as violet, while radiation in the wavelength of 700 nanometers appears red. The different colors of the rainbow, red, orange, yellow, green, blue, violet, are arranged in descending order of their wavelengths. Roughly, we can break down the various colors into the wavelengths band as follows. 400 to 40, violet is 400 to 440, red is 650 to 700, and everything in between. Radiation below 400 nanometers wavelength is called ultraviolet radiation and is typically divided, that is that to the left over here, that's called ultraviolet, and is typically divided into three segments: UVA, UVB, and UVC. Ultraviolet radiation is not visible to the human eye, but it can have damaging impact on humans as well as corals. The ultraviolet A segment is the most common in sunlight. That is the one closest to violet. Overlaps slightly with the shortest wavelengths in the visible portion of the spectrum. UVB is effectively the most destructive UV radiation from the sun because it penetrates the atmosphere and can injure biological tissues. UVC radiation from the sun would cause even more injury, but it is absorbed by the atmosphere, so it almost never reaches the Earth's surface. Now, the reason I'm reading this so quickly is because this is all information that I already know. I didn't know that it was divided into three little segments, but those are pretty arbitrary, really. The question I'm really looking for, which I thought that the title of this this article was going to push me toward, was the spectral distribution of LEDs. So I thought I was going to see several examples of different LED lights and find out what their spectral distributions are. And here it is, spectral output of the different LED components, Radion XR30W. What's that mean? The Ecotech Radion is one of the few LEDs that offers multiple color LEDs with two types of LED, blue, white, green, and red LEDs. Okay, so this is a comparison of radion, which is this red line here, compared to radium 400WHQI, which produces a huge bunch of its light right at 450 micrometers, and Ushio 14K 400W, which actually manages, I think, what looks to be a more even distribution of wavelengths. And then they have the radion LED spectrums, and these are different colors of, I gather these are several different LED samples that they've manufactured. So they have the all spectrum, the white spectrum, the blue spectrum right here, and the royal blue spectrum. Oh, maybe that's the royal blue, and the green spectrum, and the red spectrum. But then it says spectral output of the radion XR30W compared to the metal halide. Now, I have a feeling that none of this is going to explain why LEDs in general have a better power, have, use less power than, LEDs use less power than CFLs. If that's true, the reason that one bulb uses less power than the other is not going to be seen in the visible spectrum, but in some other spectrum. So I should be searching for something like infrared spectrum of CFL versus LED. And here is what we've got. Diagram of the spectrum of the LED lamp blue versus the CFL green and the incandescent purple light. Where's the purple? Purple is up here. Superimposed on the solar spectrum in yellow. Now, to me, it looks like in each case, there's hardly any wasted wavelengths. Maybe the CFL. Let's see if. So I'm trying out the eyedrop tool to see if I can match the color to these. CFL is this blue line. LED is the green line. The solar spectrum is this yellow. And the incandescent spectrum is shown in whatever color that is. Incandescent light is actually obviously using up a lot of its energy, most of its energy in fact, producing light in the infrared, light that we don't see. It also wastes some energy producing light in the ultraviolet. On the other hand, both CFL lights and LED lights manage to stick pretty close to the visible spectrum. In other words, they don't waste energy producing light that humans can't see. Alright, I wanted to give a kind of a comparison of two things that seem kind of unrelated, but 1 watt per square meter of sound and 1 watt per square meter of light. Usually we don't talk about the wattage of sound per square meter. This would be called the intensity of sound, and 1 watt per square meter is 120 decibels of sound. And I can't remember whether this is deafening or if it's just the pain threshold. It looks like it is the threshold of pain for light, yes. Now, let's compare that to 1 watt per square meter of light. Let's take a 13 watt CFL bulb, which would look something like this, because those things have those weird squigglies. And we'll just make that a 13 watt. I don't know why it's that color. Oh yeah, because of the color of this graph up here. Okay, sorry about that. But yeah, the light bulb, and I think I'll just draw the old-fashioned kind of light bulb because that's easier to draw. But I'll draw a squiggle in it as a rough symbol for it. We have this 13 watt bulb, and it is being distributed over, say, a radius of 1 meter. Now, what is the surface area of that surrounding sphere that is 1 meter around? The surface area is A equals 4 pi r squared. In this case, it's radius of 1, so it'll be equal to 4 pi times 1 meter squared. And so 4 pi is about 12.566 about, yeah, right. That's pretty specific. It's about a surface area of 12.56 meters squared. It's about 13 meters squared. So that's kind of convenient because a lot of the CFL bulbs that are equivalent to 60-watt incandescent bulbs are usually measured in 13 watts. So if we took 13 watts divided by 13 square meters, we get about 1 watt per meter squared. So looking at a 13-watt bulb from 1 meter away is about the equivalent of the intensity of sound at the threshold for pain. And I think that's kind of apt, because if you actually do, if someone actually would, and I don't recommend it, stand and stare at a bare 13-watt CFL bulb from a distance of 1 meter, you will find you will probably get a headache. You will get you will have that after image in your eye of the light that will last at least 5-10 minutes after, if you keep that up for very long, and it's going to cause some damage to your eyes, just as listening to 120 decibels of sound would also cause some damage to your eyes. No, it would cause damage to your ears. On the other hand, if you held your ears firmly shut and stood in a room with 120 decibels of sound, well, that's going to get through your probably going to get through your fingers and still cause some discomfort. But if you are sitting in a room 1 meter from a bare incandescent light, it's really not going to do anything to your skin. It's just where the particular rods and cones of your eyes that are susceptible to those particular frequencies are hurt, just as if you stood in a room and it's just your ears that are affected by the 120 decibels of sound. Let's look for a comparison of a low wattage space heater. What if your intent is completely not creating visible light, but creating heat? Well, here's a 400-watt wall panel heater. That is considerably more than that 13-watt light bulb. Here's the Vornado desktop heater with settings of 375 watts and 750 watts. So how does this thing change its settings? How is it able to decide? How are you able to flip a switch and say, okay, I want it to operate at a 375 watt level or a 750 watt level? Well, electrical sockets in the United States typically supply electricity at between 110 and 120 volts AC. And if you're plugging in an appliance that is compatible with multiple voltages, then an adapter is all you need. Now that 120 volts AC is ran through some kind of circuit, including, I don't know, diodes and resistors or something like that, and somehow becomes, and I'm drawing, vaguely remember something that looks kind of like that, but I think it may have been in a dream sometime. Or I may have Googled sometime an AC to DC, let's see, power converter. Anyway, that 120 volts AC is generally converted somehow to basically what essentially looks like a 120 volt. Well, we can think of it, whether it actually is this or not, we can think of it as a 120 volt DC voltage supply. If I run that across a 1 ohm resistor, that is going to produce a current. I equals V over R is going to be 120 amps. And it's going to produce a power of 120 amps times 120 volts, which is some extraordinary, crazy, excessive 144. 12 times 12 is 144. Then I'll put two zeros on that. That's going to produce 14,400 watts of energy. In fact, you can simplify this into a formula that goes power equals VI equals V squared over R. Since I is V over R, you can just say power is V squared over R. So if we've got this Vornado desktop heater, we can actually calculate. Basically, we're swapping two resistors here. The power equals V squared over R, or R in turn equals V squared over power. So we're going to switch between we're going to keep the voltage the same. So in both cases, the resistance is going to be 120 squared divided by our internal resistance, or our power, desired power. So 375, we'll use a resistor of, we'll have a resistance of 38.4 ohms. On the other hand, if we want a 750 watt power supply, we will take 120 squared divided by 750 and find that the resistance is 19.2 ohms. So here's some pictures of heating elements for an oven on Google. Here's an image from a YouTube video telling how to replace the heating element. Okay, I'm not sure how close this will come out to be the reality, but I'm going to make this bold statement here that the power over a unit area is equal to sigma T to the fourth. This is the power of a blackbody spectrum. Sigma is called Stefan Boltzmann's constant, and it has kind of a funny sing-song numeric value, 5.67 times 10 to the negative 8th. 5678. Anyway, it's in, well, you can see it from here, watts per meter squared Kelvin to the fourth. Whoops, no, watts per meter squared per Kelvin to the fourth. And that just makes the units on the other variables come out right. So if I stick in a temperature of Kelvin, I could actually take one of those heating elements from the oven, find out what temperature does it get to, and then find the surface area of that whole tube, which is going to be pi 2. It's going to be the circumference, which is 2 pi r times its length, and that's the surface area. So I could actually predict the power coming out of it from the amount of temperature. What are we going to put it on? 400 degrees Fahrenheit? Let's see, 400 degrees Fahrenheit is 368 degrees over the temperature of freezing water. And there are 100 degrees Celsius for every 180 degrees Fahrenheit. So that's 204 and 4 ninths Celsius. But I'm then going to add 273 to that to get it into Celsius. I'm sorry, Kelvin. So 400 degrees Fahrenheit is about 477 degrees Celsius. So I could actually find out if all of that temperature, or if the temperature of the oven should be equalized. So this probably is producing approximately a temperature of 477.54 degrees. But the power that is coming out of it is going to be 2 pi r L times the times that sigma, 5.67 times 10 to the negative 8, times that 477 to the power of 4. Let's just make this a little bit easier on ourselves and just figure out the intensity rather than the power. The intensity is going to be just sigma times 477 to the 4th. So that 5.67 times 10 to the negative 8 times 477 is to the 4th, sorry, second enter, to the power of 4, and we get 2,935 watts. No, that's watts per meter squared. And so in order to find out how much power we really need to do that, it's going to be more than 2935 watts. We've got to actually multiply that by the surface area of the material, which is 2 pi RL. We could measure the radius or the diameter of this and the length of the heating element and find out how much power it took and how much resistance would be needed, which was V squared over the power that is required. And so question I have now is, how do they control the resistance of this thing in order to set the outcoming temperature? I think it's basically some kind of resistance control that would determine how much power is going into it, and that basically by changing the resistance you're able to change the amount of power coming out. Thanks for watching my disorganized video on power resistance. I will talk to you later.